Okay, so we are continuing our discussion on non-linear transform, and then now we'll talk more about generalization because that is the eventual goal, right? So let's talk about generalizations and some more practical issues as well, like how to choose a feature transform and so on. What are the different factors that impact our selection of which model we are going to go with? Okay, so now we have the X space, which is X is the augmented one. And then of course you have the D dimension, and then we have the Z space. So the Z space pretty much similar in the sense that we have the new created variable that has 1 and then R, and then we said we'll everything in the new feature space we will denote by D tilde, so that's that. Now if we talk about the VC dimension for this one, that's going to be D plus 1, and if we talk about the VC dimension for this new space, it's roughly this. Okay, so basically what we're trying to say is that the same theory that applied to this X space now also applies to Z space, which means this equation of E out G less than equal to E in of G plus the error bar, which is, I'll just write of the order of D tilde over N log of N still holds, right? So basically the error bar is related to the dimension of the Z space as well. Now what should this D tilde be, right? That's what we are interested in, so that we get a decent like relationship between E out and E in. So the question that we're trying to answer is, what should this D tilde be, correct? Okay, so for obviously we want, I would say we would like or we want this D tilde to be small, because then it gives a better, tighter relationship between E out and E in. So basically we want this D tilde to be small. Because this implies that my E out is indeed going to be very close to my E in, right? So how can we achieve that? Well, I will try to go to the lowest dimension possible so that I can get my E in equals 0. Like I would say combine the two, because I'll try to get the lowest dimension while getting E in close to 0. And this way you will have the tightest link between my E out and E in. Okay, so how do we achieve that? How do we get that? Well, there can be multiple ways of doing it, and many, as I said, many non-linear transforms can work. If you remember, this was one of the examples that we looked at earlier. So let's say this is my X space, and then I'm trying to come up with my Z space, right? So this is a possibility, this is a possibility, and this is a possibility. What is this possibility about? Well, I've defined two variables, Z1 and Z2, and because I can see that this can, like, there is like this effective hypothesis that is nothing but the equation of a circle. So just by looking at that, I can create this variable Z1, as you can see here, right, which is equal to x1 plus 0.05, just like slightly less than this, so it keeps within the boundary, right, and then square that, and Z2 is going to be equal to x1, which is, sorry, x2, right? This dimension stays the same, and so you can see like these points just like fall here on this side. Well, this also looks good to me because then I can separate them somehow like this, right? The other one is the one that we took the liberty of taking and then analyzing it. So this is the second one. So obviously I can have a linear separator here. Good news, right? And in both these cases, I have like two-dimensional space, right? So I have two-dimensional space where I have just changed based on some phi. That is my nonlinear transform. Well, look at this one. This is even better because I've converted everything into one-dimensional space. Right, look at this one. What I did was I defined a variable, new variable obviously, Z1, and I just looked at this equation, which was fitting my data really well. And then I decided, how about my z1 is going to be x1 squared plus x2 squared minus 0.06, comes from here, right? And that helps me because why? Everything on this side, on the left-hand side, that's less than this, is going to be of one category, like everything within the circle is going to be one category, everything outside is going to be something else. So basically I can translate all of this in a single line. Right, so this made my job really easy because this is perfect separability in one dimension. So basically the VC dimension in this case is going to be 2, which is, I think, the tightest possible link that I could think of. Okay, so all of this sounds really great, but do you think there is any issue here? Well, the issue that I think everybody's been thinking ever since we started talking about nonlinear transforms, and that is I already looked at the data, right? I looked at the data, and let me write it down. We looked at the data, and then based on that, we decided these transforms. If you remember, the way we built the theory was that you are not allowed to look at the data because you cannot tailor your final hypothesis set. And so you cannot look at the data before you pick the hypothesis set, which in turn is the feature transform. So we cannot do this. Whatever we did here on this slide, we cannot do that. Okay, so having said that, what exactly can we do? How can we use feature transform in practice? Okay, so how to use feature transform in practice? Well, that's a very important question because until now we are being a little suspicious in the way we have tried to look at everything, but now we are going to answer all those questions. So the first thing is we must choose, so we must choose the nonlinear feature transform before we see the data. Okay, so how do I know if I need it or not? That's the next question, because like the way we analyzed it, at least the thing that came out is that we already knew the data, and then based on that we came up with this like z1 squared and sorry, x1 squared and x2 squared for z1 and z2. But that is not applicable in practice because the theory falls apart. That's not allowed, right? So how do I know if I need it? Maybe I would say domain knowledge, right? Maybe domain knowledge, maybe feature construction, again depending on the knowledge that you already have, or like in the credit example, we knew about saturation, the phenomena of saturation. But like honestly, we cannot be all the time sure, right? There might be factors that I'm unaware of, right? Maybe I know that I need a little bit of flexibility in my model, and then we can just like keep thinking about this on and on. So what is that like set procedure that we should use in order to come up with like which feature transform should I use? Because there are so many, apart from like the ones that we looked at here, there are so many feature transforms that are available. For example, polynomial of any degree, sinusoidal, Fourier, etc. So I don't know which one to use. So let us assume that there is one go-to solution for everything, and that's my polynomial feature transform. So this is the one that is going to help us answer all those questions. So let's look at this polynomial feature transform. Okay, so what is it? Well, let's illustrate that in a two-dimensional space. So let us assume it's a two-dimensional space, and my data is something like this, 1x1, x2, and then I apply a polynomial, and then I'm denoting it by phi, and 1 means polynomial of degree 1, and obviously this transformation means nothing, so this stays as it was. It stays as it was, and there's basically no need to transform. And the VC dimension for this new transformed space is 3, and it's a two-dimensional input space, but the VC dimension of this one is going to be 3 because we have like 3 of these. Okay, so similar to that, I can apply a quadratic, a degree 2, right? So maybe I can write it degree 1. Then I can apply degree 2. So let me do that. Degree 2, phi 2. And what happens in this quadratic degree 2 transformation? Phi 2 is going to do that. So basically, I will include all the terms that are below that degree. So for example, degree 2, so degree 1 will also be included, x1, x2, and all quadratic terms will be included. For example, x1 squared, x2 squared, and then x1, x2, and that's it, right? So all quadratic terms, and the VC dimension of this like new space, because I've applied phi to it, is going to be, as you can tell just by looking at the new dimensions, so this is going to be 6, right? Okay, so similar to that, let me apply the same input. Okay, this has to be 1. And degree 3, phi 3, and this is going to give me all the terms up to the cubic terms, right? So 1, x1, x2, and then similar to this, let me just like copy this first, x2 squared, x1, x2, and then all these terms as well, right? So starting from x1 cube, and then x1 squared, x2, x1, x2 squared, right? And then x2 cube, yeah, and that's it, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so where should I write my d tilde VC is going to be 10. And similar to that, I can keep like going on and on. And in fact, for the 4th degree polynomial, you can just like go ahead and do that. If we do that for the 4th degree, so it'll include all these terms. And then if you just think about it, the 2 4 degree terms, and then 1, 2, 3. So basically you will have 15 terms, right? In the 4th degree one, the VC dimension is going to be 15 and so on. Now, this is actually like more of a counting problem. So the polynomial transform of degree q for an original x of t dimension, because this was like a 2 dimension. So let's say we are interested in finding the polynomial transform of degree q such that the input is degree d. Right, so how can we find the number of, how can we calculate the VC dimension? So basically what we are trying to do is this D dimension, like this D is going to be Q plus D, choose Q. And D of course is going to be 1 less than that. Now, if you think about like the dimensions growing and also the Q growing because the degree of the polynomial growing, you can tell that this is going to be a huge value. Right, so basically the VC dimension is going to be a huge value as we increase, as we have more dimensions in the data and as we have like a greater degree polynomial. So what does that tell us from the theory? Well, that tells us that we are kind of losing control of E out, right? So this relationship between E in and E out through the error bar is becoming loose, right? It's no more a tight control. And so we're losing that, and then if you're losing that, that's the whole point of solving any machine learning problem. It's not enough that we have an E in equals 0. We need to maintain that relationship between E in and E out because that's the whole point of solving any machine learning problem. Okay, so what should we do? What is the overall like recommendation for anyone? Now, one recommendation is like if the problem needs flexibility, and you think you cannot do it with a linear model, go to the 2nd degree feature transform. So if you think about the original example that we have, just go to this, try the 2nd degree polynomial, and then try to fit, well, I'll not know that, and we cannot, as I said, decide before looking at the data. But if you have like a feature, you have created features, you have feature construction done, and you have some domain knowledge, and you know that this is like you need more flexibility in terms of the problem itself, and you think linear is not enough, then the second choice should be the 2nd order polynomial because most likely that is going to help. But then that seems reasonable, I would say, as you can see in this picture. Well, but many times we have really complex data, and the problem itself, if whatever knowledge we have of the problem, we think that this is going to be really difficult. So why not try and use 4th order polynomial, let's say, in any given problem? Why don't we look at the problem that we looked earlier when we were allowing for some error for the linear model. So if you remember this one, so let's say this was my data and I decided, let me use a polynomial of the order 4, right? Fourth order polynomial basically. So I did that. So this is the fourth order polynomial. And you can see, well, here we were tolerating for these errors, right? And here I don't have to do that anymore. Wow, it fits like really well, although it has like this complex, I don't know, shape, complex way of like categorizing data, but it is doing it. So basically what I'm getting is an E in really close to 0. Isn't that a good thing? Well, there are a lot of bad things here, more than the good things that we can see. So what is wrong? Well, the first thing, and do not get confused yet, so we are seeing something that's known as overfitting. I will talk in detail about it in the next lecture, so we don't have to really worry too much about it. But what it's saying is that if we overfit to the data that's given to us, then that's a bad sign for the new data, which means that this is not going to work for the new data. So that's like the general idea of overfitting. Let's not go into too much detail. The other thing that we already know is that we are losing control of E in being close to E out, because we have the fourth order polynomial, and so you know that the VC dimension must be like 15 or 16, I think 15, right? And so the theory is itself telling us what this overfitting phenomena will also tell us. So theory is anyways indirectly pointing us to the fact that I fit a fourth order polynomial, which might seem really good in terms of the data that I have, but well, not quite. Okay, so what should we think about when going for a linear model versus a fourth order polynomial, and whenever we are in a predicament like this? Let's look at another example. This is the digits data again. Okay, so if you remember, we came down to 2 dimensions in this case. We did some feature construction. So we did feature construction, and then we came up with these two features, symmetry and intensity. And here we are using the linear model, right? And you can see the value for E in and E out. And as is evident, right, there is a tight link between E in and E out, because my this is a simple model. I don't have so many dimensions, and the Q value is also low, so that's good. Now, if I try to fit the third order polynomial here in this digits data itself, well, you can see that it's fitting better, right? It fits better, much better actually. And then there are fewer misclassified points because it is including some of those like the ones at the borderline, right? And maybe we can say that like there is a reasonable link between E in and E out, although we are using this higher order polynomial. But this link is a result of not just the dimensions of the third order polynomial, but also because we have a large amount of data in this case, which means my n is large. So that's also impacting this relationship. Although like in terms of the accuracy, like how close I got to E out, there is like overall an improvement of 1%, right? And 1% improvement as compared to the linear model. So now you can say that this is surprising because we did so much for this, like to get to polynomial transforms, right? And we did so much and we just got like 1% improvement. So the answer, so like the question that you should ask yourself is it worth it? Like in terms of the problem, in terms of the problem that you're trying to solve, in terms of the business to which this is going to be applied to. That's the fundamental idea of whether we should be using the nonlinear transform or not. That is the fundamental idea, whether this 1% is worth it or not. Because like in many situations, this might be worth it, right? This might be that this is like really important to the business and that 1% really translates to something, some huge improvement in something. And so, yeah, go ahead and use the third order polynomial. But in most of the situations, in most of the typical machine learning problems, like the linear model would do really well, pretty well, as you can see even in this case. And the good thing with the linear model is that it is going to do pretty well and also maintain this relationship. So it is not going to get into that bound getting loose, essentially. So that's the fundamental idea. Whether to choose or not depends on your problem, depends on how much data you have. For example, here n is large, and so that's why we are still seeing a good link between E in and E out. And of course, there is an improvement also in E in and E out, and as we said, the accuracy has improved by 1%, that's it. And so then it depends on us whether we want a more complex model or not, and also depends on the problem, like maybe moving to a more complex problem, well, it pays off. For example, let's look at the credit card problem. Well, if my data is distributed something like this, and let's say there are lots of like cases in the borderline, right? And yeah, let's say this one is also this and this. And so if you had something like this, that really kind of, divides the space better as compared to a linear model. And if it really mattered to the business that these borderline cases are really important, then maybe yes, it makes sense to use a higher order polynomial, maybe use the transform. If not, then the linear model would, I would say, with a slightly less accuracy, it would still work pretty well. So again, it depends on a lot of factors. It depends on how well you have captured the data, how large your n is, and so on. Okay, so having said that, this is the concluding slide, and it obviously recommends use the linear model. So if you really understand your problem well, linear model should work in most of the cases, in most of the situations. In most of the cases, linear model should work really well. So always try, this should be the recommended methodology. This is the recommended methodology. Try a linear model. It's simple, it's robust, works, creates a tight link between E in and E out. We don't have to worry about that. And next, we have algorithms that can tolerate error plus, for example, the pocket algorithm, right? So we are tolerating some error, and then we are also achieving efficiency, and we're not getting too much into the, I would say, the complexity of like the nonlinear feature transforms, especially the higher order ones. But then remember, you have the nonlinear feature transforms as well. So again, analyze the problem well, and then based on that, make the decision. Okay, the next thing is choose a feature transform before seeing the data. This is extremely important. Whatever we did in this lecture was more from the perspective of analyzing what happens when you chose a feature transform and how is it useful, right? But it was never the case that we wanted you to look at the data and then choose based on like whatever you see. So that wasn't the intent. So always choose a feature transform before you see the data. Stay as simple as possible. Again, the recommendation is second degree, maximum third degree polynomial, depending on how much data you have, depending on how important the problem is with respect to the business. So data snooping is not allowed. I would say this should never be done. Again, reiterating the advantages of linear models, they are fundamental in their own right. They are essential building blocks for all complex models, most of the complex models that we are going to look at. For example, support vector machines, I think it's coming up real soon. So we'll see how linear models build those, and then also the neural networks. Finally, these nonlinear transforms can also apply to regression and logistic regression problems, just like we saw for classification problem, but it is equally relevant, applies to both two large categories of problems, the regression and logistic regression problem set as well. Okay, so with that, I'd like to end this lecture about nonlinear transforms, and thank you so much for watching.